In calculus 1, or even in algebra or trig, when you had a curvature surface and you went to measure the length around it, you called it the arc length. Here in the 3D space, we call it now the surface area. So basically what we're going to do is we're going to find the arc length over one curve, and then we're going to add up through a summation process all of those curves if I keep slicing and keep adding. So basically you have the summation of these. One integral finds one of those arc lengths, and then it begins to measure those guys, and then that second integral takes the width of it and measures that. So we have this length times width, the length arc length, the width arc length, and then you multiply those two together, we get this double integral. So basically this surface area that we're dealing with is no more than a very fancy arc length formula that you've looked at even back in calculus 1. Okay. What I think is so phenomenal with the mathematics, and to really talk about how powerful the tangent vector is, this tangent vector, this capital T, is that gradient. Okay? So it is so powerful that if I look at its delta, it's approximated here to be the surface area itself. So in calculating the surface area, all we're doing is actually approximating the double integral over the tangent. That's very, very fascinating. Now the question is this surface area, take some surface and look at it at a particular point, is that the same as its tangent? Well, if that tangent vector, if it's enlarged, you may say, no, that's not, because this tangent vector is going to give us a plane. Right? It's going to be a plane right there at the curved point. But we take the limit of this tangent, and it gives us that area right around the point, which I can be very precise in calculating all such tangents along the surface. So the surface must be continuous, and all the partial derivatives must be continuous as well. So we call it that the surface must be a smooth curve. Let's look at the formula, and the formula, when you see it, you should make the connection with the old-fashioned arc length. So let me scroll down first. So here, you recall the integral for the arc length, which we talked about. That was calculus 1. You talk about the area for a region in the XY plane. Talked about this in sections 14.1 and 14.2. So we have this double integral over a region with respect to the change in the area. But to talk about the so-called surface area, I want to go above dA, so we talk about the change with respect to the surface. So I bring it up. So when I bring it up, I begin to calculate here the arc lengths. The arc lengths with respect to x and also with respect to y. You add all those up with respect to this double integral, and we get the area along the surface. Do you see how from calculus 1 we have this single integral, this arc length formula? You see how similar that is to now in calculus 3 with this double integral for the surface area? You see how the formula here is given as well? Let's see where it comes from. let z equal to f of xy represent a surface in the third space. Here we set capital F to equal to f of xy minus z. In chapter 15, we'll call this capital F capital G, but talking about the same representation. If I take the gradient of F, here this gives me the partial of F with respect to x, xy, I, plus the partial of F with respect to y at the point xy, j, minus, here take the partial here with respect to this z, we just get 1 times k. If I take its gradient, I get the square root. I'm going to just go ahead and deal with this negative 1 to be squared. That just gives me a 1 plus the partial of f with respect to x at the point xy to be squared, plus the partial of f with respect to y at xy, that guy to be squared. So this surface area is equal to this double integral over the region with respect to the change in the area. This is reduced to this double integral over the region. This ds becomes this gradient, the norm of the gradient of f times dA. And this norm of that square root, that's exactly the formula that's given above. That's it. Right. Okay. Let's see. Why are the first partial derivatives, why are they continuous? Because here we're trying to approximate this change in the surface with the change in the tangent. Right? What tangent vector is that? It's this guy right here. Here, to get this term, we take its norm, by all means. Why the norm? Because I actually want to measure the length of something. Right? Let's see. Find the surface area given by z equal to f of xy that lies above the region R. Here, this region, this is a plane over this square with vertices given. Let's see, this is in the xy plane, so something's happening above it. It's this function f. And so this says here for R, x goes from 0 to 3, and y goes from 0 to 3. We need those partial derivatives. Partial of f with respect to x is 2. The partial of f with respect to y is negative 3. So the surface area is this double integral. Here, x and y both go from 0 to 3. It's the square root of 1 plus 2 to be squared plus negative 3 to be squared dx dy. Get the square root of 14 times this double integral. Integrate with respect to x. So we get the square root of 14 times the integral from 0 to 3 of x evaluated from 0 to 3 dy. This gives us a 3 times the square root of 14 times the integral from 0 to 3 of dy. That'll give us a 3 as well, so we get 9 times the square root of 14. Okay. What good is the surface area? Chapter 15, we talk about something that's a little bit more important than this guy, I think, and we call it the surface integral, which takes the surface area and it adds another component to it. The surface integral is needed for the fluid flow. And that's what we're trying to get to. Yes, sir. No, 0, 0, 3, 0, 0, 3, and 3, 3. Right? 0, 0 is there, 3, 0, 0, 3, and then 3, 3. Yes, sir, I'm sorry. Yeah, the function f. Yes, sir. Now, we need those partial derivatives, right? So the partial of f with respect to x is 5. The partial of f with respect to y is 6. For that region, you need lower and upper bounds for x, lower and upper bounds for y. What would be easier there for our region R? Pardon me? You got to find the surface area, right? Well, one component of the surface area is to find those partial derivatives. The other component is to find the area, dA. The area is based on the region. What's the region? Okay. Is that thing right there? Yes. That region is this circle, right? What's happening inside that circle? X squared plus y squared less than or equal to 4. How do you represent that for bounds for x and y? I do too. I'm just. Man, I tell you, Donnie, you make a person who don't smoke want to smoke. Where's that train again? They had that pot on that train. Where is that train? Hey, look, don't tell my church that. But anyway. Oh, man. you can find the region. Say, for example, you can use -4 less than or equal to. Too big. And then for y, negative square root of 4 minus x squared less than or equal to y less than or equal to the square root of 4 minus x squared. And when you integrate all of that, you're going to have to use a graphing calculator, trig substitution, or something like that. Or Mr. Tuggle was trying to tell us that we can convert to polar coordinates. Anytime you're given the region, if it's a circle or part of a circle, you always go, it's easier to polar coordinates. That was the whole reason why we had the previous section. Right? Yes, sir. So you look at that circle, radius 2, so r goes from 0 to 2. It's the complete circle. So 0 less than or equal to theta, less than or equal to 2 pi. This coordinate system, the polar coordinates, will be a whole lot easier to integrate versus this rectangular form here for x and y. Okay? So we have this double integral. I have that square root of 1 plus 5 squared plus 6 squared. This is r dr d theta. R goes from 0 to 2. Theta goes from 0 to 2 pi. So on the outside, we have 25 plus 36 plus the 1. And then we integrate. We get r squared over 2. R goes from 0 to 2. D theta. What is that? The square root of 62? 62. Yeah. And then this is times r, which is 2 to be squared over 2. That integral from 0 to 2 pi d theta. So this gives us 2 times the square root of 62 times theta. Theta is evaluated from 0 to 2 pi. So we get 4 pi times the square root of 62. Okay. All right. All right, we're close down to the end. I think you can do this one. Set up very similar to that previous one, right? Sound about right, John? Yeah. Got that, India? That? Good. Ryan, you got it? No? Uh-oh. Did you get the square root of 14 for that radical? Donnie, you got it? Okay, you got that one. Okay, good. Remember, it's the square root of 1 plus the partial of f with respect to x, that's squared, plus the partial of f with respect to y, that guy is squared. And then times how you define dA, the area. The area is based on the region. The region is a circle with radius 3. It's a complete circle. Right? It's the square root of 1 plus, this is 4 plus 9 times r dr d theta. So you integrate that, you get 9 over 2 times the square root of 14 times the integral from 0 to 2 pi d theta. So that gives you 9 over 2 times the square root of 14 times 2 pi. And that gives you 9 pi times the square root of 14. All right. Okay. Got 7 minutes, 8 minutes, and I have 2 problems left. So I'm going to skip this one. This guy is good. You work that, and let's see what you get. Oh, let me define this for you. See if I can help you out on this one. I'm sorry. This is f of r theta. I'm going to convert this function f to polar coordinates as well. This is just r. And so what I have is this capital F, which then looks like this r minus z. So this gradient of f is with respect to the r. This is I. And then theta, there's no theta. Then the z is minus k. And so that gradient, the norm of the gradient of f is the square root of 1, the square root of 1 to be squared, plus the square root of that negative 1 to be squared. You get the square root of 2. And the region here puts this square root of x squared plus y squared in the middle between 0 and 1. The surface area is this double integral over some region r. The square root of 2, we have here r dr d theta, right? So theta goes from 0 to 1. excuse me, that's r goes from 0 to 1. Theta goes from 0 to what? Is it pi over 2? F of xy is the height, but in terms of x and y, what can x and y be? It says, the region here, it says for all x, y such that the function values are between 0 and 1. The z values are between 0 and 1. What's the restriction on x and y? So it goes to 2 pi. Yep. Okay, I'll let you finish that one. But that's the setup for it. So it takes all the work. Should get like, I think, pi times the square root of 2 when you work that one out. Let me go to that last one and work that one out for you. I define r as being, well, f as being r cosine theta times r sine theta. I would not have done this unless r was given as some part of a circle. See that? So that tells me that I can convert to the polar coordinates. This region goes from 0 here to r less than or equal to 4. And then theta, well, that's the complete circle, so theta goes from 0 to 2 pi. Give you a couple minutes to see what you can do with that one. You may want to do this. The partial of f with respect to x is y, and the partial of f with respect to y here is x. I'm going to show you a trick. This is 1 plus x squared plus y squared times r dr d theta. R goes from 0 to 4. Theta goes from 0 to 2 pi. Now, I can't integrate that the way it is because I have a mixture of terms. I have x, y's, and r. But that x squared plus y squared under that radical is just r squared. This is the double integral of r times the square root of 1 plus r squared dr d theta. Here r goes from 0 to 4, and theta goes from 0 to 2 pi. To integrate that, you have to let u equal to 1 plus r squared. Du picks up the r on the outside. Okay. Two r dr, excuse me. And that's my time, so I think there's a class coming in. But you can finish that. Let me know what you get on tomorrow.